Yes,
Yes, we can see your mouse.
I see your
Yes.
mouse.
This you can see here the 6 oscillation parameters, 3 of which are well measured, including the solar mixing and the reactor mixing parameters, and the solar splitting. They are indicated in green. In contrast, you have 3 poorly determined parameters. First of all, the mass ordering problem. We cannot distinguish, I mean, both normal and inverted mass ordering give a viable solution to the oscillation phenomenology, and they are indicated by the blue and magenta curves. That's why we always have 2 curves. They are about 3 sigma apart, so both descriptions are acceptable. Then we have the ambiguity concerning the ordering of the atmospheric mixing, determination, and finally, we have a very poor CP determination, especially for the preferred case of normal mass ordering. Besides the individual determination of the oscillation parameters, which I have arranged here as the diagonal entries of this triangular matrix, we have all pairwise oscillation parameter correlations, which are shown as the other entries of this correlation matrix. This matrix is very important because it provides the full information given by the oscillation experiments, and it's very useful for model builders. If you are studying predictions from flavor theories, they are bound to be a few entries of this matrix, and you can get all the relevant information by just clicking to this website. You get all the tables which are used in order to provide all these the correlation plots. In particular, the square that you see in red color, I call it the ignorance plane because it puts together the most poorly determined of the oscillation parameters, namely the CP phase delta, CP, the atmospheric mixing for each of the allowed mass orderings. So this is the complete map of neutrino oscillation parameters. And all in all, the oscillation picture is quite successful, is quite consistent, but there are these 3 issues that need improvement concerning, as I said, the mass ordering, the octant determination, and the CP. And these actually form the target of the next round of neutrino experiments. So here I'll start with the case of CP violation, and I show the cartoon for the deep underground neutrino experiment, DUNE, which will study neutrinos produced at the Fermilab accelerator complex and detected 1,300 kilometers away at the SURF facility, which is exactly the same mine complex where Ray Davis pioneered his solar neutrino studies back in the 60s. Okay, so DUNE offers this sensitivity indicated by the black curves to the CP violating phase delta CP. So you can see that the sensitivity can exceed 5 sigma. And besides the black sensitivity forecast, I also show the expectation that would come from the case where unitarity is slightly broken in the lepton mixing matrix, as expected, for example, if neutrino masses arise from a type 1 low-sky seesaw. So these would be deviations of 1, 2, and 3% of strict unitarity of the lepton mixing matrix. This is for the DUNE experiment. There is the most serious contender of DUNE is the Hyper-K experiment. And I should advertise also that in Europe, we have the neutrino superbeam experiment using neutrinos from the European spallation source is also sensitive to CP violation, as you show here, and I would say, in principle, could provide quite competitive results with those of Dune. The mass ordering is another issue, as I explained. Here we expect improvements from the Juno reactor neutrino experiments, which should be starting rather soon. Unfortunately, though, Juno by itself will not settle the mass ordering problem, but in combination with results from long baseline neutrino beams and possibly from neutrino telescope will substantially will give substantial results for the mass ordering discrimination. So let me now turn to neutrinoless double beta decay. This would be a process in which two neutrons beta decay inside a nucleus, so that the antineutrino emitted by one beta decaying neutron gets reabsorbed by the other proportionally to the light Majorana mass of that neutrino, and that just comes from the Majorana propagator. So the relevant amplitude I call m beta beta for neutrinoless double beta decay, which for short I will just call DBD in what follows. It involves, besides the two mass parameters that are well measured in neutrino oscillation, it involves the third mass parameters because all the masses take part here in the propagator. Moreover, it involves, in a crucial manner, the two phases phi-12 and phi-13, which are Majorana phases and which are totally inaccessible to oscillation experiment. I should also stress that this description is based on the original symmetrical parametrization that we proposed back in 1980, and which is far, far neater for this purpose than the phase convention chosen by the PDG much later. So the task, our task here is to determine, taking into account the oscillation experiments, what are the allowed values for this amplitude m beta beta. And this is shown here in this plot, which is given in terms of this dimensionless parameter eta, so that when eta is 1, all neutrinos are degenerate, and this will give the maximum m beta beta entry. This is, of course, already ruled out by the Kamlan-Zen experiment. And so that this situation is ruled out. Moreover, cosmology rules out a much broader vertical band around this point, which is indicated here by the band, so that altogether near degeneracy of the Majorana neutrinos is severely disfavored by current observation. You also see that the allowed ranges for m beta beta must lie, they don't cover the whole plane. They must lie either in the NO branch, which would correspond to oscillations with normal mass ordering, or, which is the preferred case, by 3 sigma. But in this case, unfortunately, m beta beta can vanish due to a destructive interference amongst the light neutrinos that are exchanged here in this diagram, or in the other branch for inverted ordering, which is indicated in the orange color. So this is completely model independent. This is the impact of oscillation measurements, or the legacy of oscillation measurement is that m beta beta must lie inside one of these branches. for which, as I just said, I took the most favorable case of near degeneracy and I ruled it out. The next favorable possibility would be one in which one of the light neutrinos is massless or nearly so. There are many models that lead to this possibility. In particular, what I call missing partner seesaw type models, either tree-level or loop seesaw schemes, but with a missing partner. There is one of the right, there are less right-handed neutrino than left. In these models, it happens that one neutrino is always massless, and in this case, one notices that m beta beta is expressed in terms of the only available free parameter, namely the Majorana phase, in such a way that there is a lower bound, an absolute lower bound for m beta beta, which is indicated by the blue band, which corresponds to the blue band up there, where there was no lower bound at all. Correspondingly, for inverted mass ordering, we must lie here in this orange band. And the good thing is that now this band is completely covered by the expected sensitivity of the next round of DVD experiments, indicated in green and yellow. What if all neutrinos are massive, though? In this case, there is no guaranteed lower bound, as you can see from this. This, by the way, is the standard presentation, not the one I gave before in terms of dimensionless parameter eta. This is in terms of the lightest neutrino mass. This is what everybody gives. You see that generically there can be cancellation, but what happens, again, as a legacy of oscillation, is that there is a pattern of oscillation. We know the values of the solar mixing, roughly, the atmospheric mixing, a bit less precise, and we know that the reactor mixing is very small, so that is a well-defined pattern. So if you try to put this pattern inside the theory symmetry framework, then it is very often the case that even for normal mass ordering, there is a lower bound for m beta beta, which I show here in this example, in this particular paper, taken from this reference, Barreiros et al., our Portuguese friends. And so you see that there is a lower bound, despite the fact that the neutrino is a normal order, the spectrum. And this comes because I'm combining, I'm making full use of the mixing pattern measured in oscillation with some symmetry principle. So that would suggest that perhaps DVD discovery lies just around the corner. I would say that even if that were not the case, it is worth the effort because of its significance. And that is established by this so-called black box theorem, which basically states that a positive DVD discovery would mean that you have a non-zero amplitude for DVD by dressing with a W boson that would always imply a Majorana mass for at least one of the neutrinos, so that you cannot escape a deep connection between DVD observation and Majorana nature of neutrino. So I now turn to theory, to the big, perhaps one of the biggest, perhaps the biggest question in particle physics, namely, what is the origin of the neutrino mass? At this point, Weinberg made a very nice observation, namely that even though the standard model lacks a neutrino mass, it has the right ingredients, namely the Higgs doublet, scalar doublet, phi, responsible for electroweak breaking, and the lepton doublet. By just stacking those together, one can form a unique lepton number violating dimension 5 operator, so that below the electroweak breaking scale, one inevitably generates a Majorana neutrino mass, as indicated by this diagram. I should say, however, that there is a misunderstanding on the minds of many people in the particle physics literature, namely that Weinberg suggests that neutrinos are Majorana because there is the dimension 5 operator. This is not really true. You can have Dirac neutrino masses generated equally well by a dimension 5 operator. So the dimensionality of the operator responsible for neutrino mass generation does not say anything about the nature of neutrino. Nevertheless, it is still interesting to note that in the Majorana case, this dimension 5 operator is unique. However, this is not a theory of neutrino mass generation. This is just a paradigm. To make any further progress, one needs a UV completion, Weinberg's argument. And from my point of view, and there are, of course, many, loop level, tree level, whatever. And this is the whole art of neutrino model building consists in filling up this blue blob in a theoretically consistent manner. From my point of view, the seesaw provide a broad class of three-level realization, UV completion of Weinberg's argument for two reasons. First of all, it opens the door for a dynamical understanding of the smallness of neutrino mass just by minimizing a Higgs potential, a generalized Higgs potential. And number two, it offers also the possibility of understanding the stability of the electroweak vacuum, by no means guaranteed within just the framework of the standard model. If you happen to be in a seesaw picture, then neutrino masses can arise in two simple manner, either involving the exchange of heavy right-handed neutrino or heavy triplet scalar bosons, so-called type 1 and type 2 seesaw. It is anecdotal here that in our early seesaw papers in Science, 1980 and 82, we were so fascinated about the simplicity of the triplet seesaw that we call this, the triplet seesaw, we call type 1. And what everybody now calls type 1, we called type 2. This is an anecdote, a piece of history. But there was an important difference between the cyan and the yellow seesaw. The yellow seesaw assumes left-right symmetry, so you must match the number of right-handed neutrino to the number of left-handed neutrino by gauge invariance. In contrast, the standard model, the cyan seesaw that we suggested, was just based on the standard model, so it's much more general, and it allows for any number of singlets, not necessarily matching the number of left-handed neutrinos. In particular, one can have a missing partner seesaw, and there are basically two missing partner seesaw. Today we know that there are 3 left neutrinos. At the time that we wrote this paper, we didn't know the number of left neutrinos. There was much before LEP, it was 1980. So we know the number of left neutrinos, but still one can have 3,2, 2 singlet neutrinos, or 3,1. 3,2 is the minimal viable type 1 seesaw, in which both solar and atmospheric mass splitting arise at 3 levels from the seesaw. In contrast, 3,1 only gives 1 neutrino mass from the seesaw. The other 2 neutrinos are degenerate and massless, so by itself it is not a complete theory, but it is just the right template to provide a complete theory for the neutrino oscillation lengths, in which one explains the observed small solar neutrino mass splitting with respect to the atmospheric one. It's about a factor 30. One explains that as a loop factor. So this is a very nice idea that one has a complete theory for the oscillation length. And an example of this theory, which I especially like, is the Scotto seesaw, because it combines two paradigms. The seesaw paradigm would be responsible for explaining atmospheric neutrino oscillation, and the scottogenic paradigm would be responsible for explaining solar neutrino oscillation. In either 3,2 or 3,1 missing partner seesaw, one has a lower bound for the DBD amplitude, which I just mentioned before, and I told you there were several examples. Here there are 2 classes of examples. Conversely, one can have a situation of having more singlet than doublet neutrino. For example, 3,6 would be a theory in which I add 2 singlets sequentially for each of the families of lepton and neutrino. In the limit where I impose lepton number conservation, the 3 doublet, mainly doublet neutrinos, are strictly massless, as in the standard model, but lepton flavor is violated, in contrast to the standard model. And in fact, lepton mu to gamma, the decay, can be huge, simply because it is unconstrained by limits that restrict the masses of the neutrinos. It's just a complementary piece of physics. This elucidates, by the way, the role of symmetry in weak interaction. Lepton flavor symmetry controls mu to gamma. Lepton number symmetry controls the neutrino mass generation. And these are complementary pieces of information. So a characteristic feature then of this 3,6 lepton number conserving template is that to generate neutrino masses, I must now break lepton number, but with an opposite philosophy of that of the high scale seesaw. Now I break the symmetry from below, using not Weinberg's naturalness criterion, but Toft's naturalness criterion. In the limit where the seed of lepton number violation go to 0, neutrinos become massless, so masses are symmetry protected. So this is as valid framework for generating neutrino masses as the high scale seesaw is. And there are basically 2 possibilities for doing this breaking, which go under the name inverse seesaw and linear seesaw. They share the same template. They share the fact that the mediator of neutrino mass generation are quasi-Dirac leptons that may be accessible to collider experiment, that whose admixture in the leptonic neutrino mixing matrix can induce unitarity, effective unitarity violation effects in neutrino oscillation, which are very important from the point of view of neutrino physics, for example, Dune, and which may also, whose exchange may also induce large charge lepton flavor violating decays. And I show this here. This is charge lepton flavor violation induced by the charge current weak interaction in these kind of low scale seesaw models. You see the expected rates can be even larger than the current limit from MEG. And you see some novel feature on the right panel, namely another type of contribution that doesn't come from the charge current weak interaction, but rather comes from a leptophilic Higgs contribution, which is characteristic of the low-scale linear seesaw mechanism. As I said, the mass of the heavy neutrino mediator is accessible, lies in the TeV range, is accessible to collider, and as I said, a common feature of both type of low-scale seesaw is that charge lepton flavor violation persists even in the limit where the light neutrinos become strictly massless. So, as I said, this elucidates the meaning of flavor violation in weak interaction vis-a-vis the meaning of lepton number violation. I now turn to dark matter. I change gears completely. This is a big drawback of the standard model. Namely, we know dark matter exists. It is lying out there, but we don't know what is it made of. The standard model offers no viable dark matter candidate. So there is a new idea that dark matter may be the seed for neutrino mass generation. I can imagine a loop in some sort of hidden sector with a singlet fermion S and a singlet scalar sigma, so that when this loop is turned on, I get a seed, I get a non-zero value for this amplitude. But now I glue this to the neutrino sector, this is nothing but the inverse seesaw. I take this seed, instead of taking SS just as a bare mass parameter, after all it is a singlet, I ascribe that small parameter to a loop. So neutrino masses are seesaw induced, but the seed is dark. So one has all the features of the low-scale seesaw mechanism that I mentioned. The mediators lie accessible to colliders, they mediate mu to gamma, they cause unitarity violation in the lepton mixing matrix, all of that. And they give a theory of dark matter as well, all together. So the neutrino mass is suppressed by the loop and by symmetry. So I have a dark loop plus a seesaw symmetry protection, a double protection. So this is a very, very natural theory of neutrino mass generation, where all the physics is phenomenologically accessible. All the particles lie in the few TeV or less. Concerning dark matter in this theory is nothing but a cold dark matter WIMP, weakly interacting massive particle, that has nothing to do with supersymmetry. It has to do with seeding neutrino mass generation, which is a completely different story. But here, this left panel show how it can give the right omega h square measured by the Planck collaboration to lie in this very narrow green band. And you can see that one can reproduce these for different colors of these, which are just different predictions corresponding to different benchmark choices of this, you may call it dark inverse seesaw model. So this is a lambda CDM model in which the cold dark matter is a WIMP. You see here, it is around 100 to GeV to 1 TeV. But this WIMP has nothing to do with supersymmetry. Dark matter is not accompanied by a whole plethora of supersymmetric states. No. And a feature of this WIMP dark matter, again, like supersymmetry, like any WIMP dark matter, it can cause a nuclear recoil. This is the cross-section for the spin-independent nuclear recoil cross-section plotted versus the dark matter mass. And you see that for different benchmark choices indicated by these different colors, one obtains cross-section values that are in the ballpark that are currently probed by the Xenon, Panda, and Lux experiments. And they can be, of course, above. Here you have the neutrino floor. In black, you have the limit from Xenon. So the interesting region is between this line and this line. And this can certainly be populated within this model in many ways. I just gave 4 parameter benchmarks. And as I said, this is WIMP cold dark matter, but unaccompanied by supersymmetric states, but accompanied by charged lepton flavor violating phenomena like mu to gamma. Completely different type of dark matter physics. Another realization of low-scale seesaw seeded by dark matter, instead of dark inverse, you can have dark linear. Again, the same story. We have this blob, and we stick this blob inside a low-scale seesaw. This blob is just that entry there in that matrix, and that breaks lepton number. These are the entries that are there in the massless template, the 3,6 model I described before, and that is the seed of lepton number violation that leads to neutrino mass. And the inverse seesaw, incidentally, will be that entry down there. So these are just alternative theories. And in fact, this linear seesaw, there is more than one UV complete realization. This is one which is published in JHEP. This is another realization by our Portuguese friends, which is published now in Physics Letters, and there may be more. So these are totally different theories. They are theories of dark matter, very much like the previous one, and very much like the previous one, instead of being accompanied by supersymmetric states, the weak dark matter is accompanied by mu to gamma processes or mu to E conversion in nucleus. The plot on the left is just the standard charge current weak interaction, and the plot on the right is corresponded to dark contribution to charge-lepton flavor violation. Okay, so much for dark seeded low-scale seesaw. Now a different game, which I already mentioned. Scotto seesaw is a hybrid construction combining two paradigms. The seesaw paradigm to explain the atmospheric, and the solar Scotto paradigm invented by these Chinese people, Ma and Tao, 10 years before Ma. They invented the same model, which is the scottogenic model. So I'm just combining the two to get a hybrid, one paradigm with the other paradigm. This way I can explain this ratio. Delta M solar over delta M atmospheric is just 3%. And this 3% is explained as a result of a calculable loop. And of course, this needs theory. And in fact, these two references provide the simplest UV completion of this argument, in which a lepton number is just a global symmetry, a spontaneously broken global symmetry. So theory is perfect, but you have to put by hand that there is only one single neutrino and three doublet neutrinos. One can be more ambitious, and this happened. Okay. This happens here, and to consider a 3,3 seesaw. So you have three right-handed neutrinos, so to say, but gauging lepton number. And there is a way to gauge lepton number using this lepton number assignment, which distinguish the third family of neutrino from the first two. And this automatically dictates that only one of the three families of neutrino acquire three-level mass, that is the atmospheric scale, produced at the tree level, and while the other two that are distinguished by the symmetry, they acquire a loop mass. And here they are. This is the tree-level mass for reproducing the atmospheric scale, and this is the loop mass for reproducing the solar scale. So this is a fully dynamical, gauged lepton number Scotto seesaw picture. What is nice about this picture is that it is a 3-3 seesaw, but it is genuinely low scale without having to go to 3,6. And the reason that works is that the VEV of this guy here, this capital phi, is an induced VEV. So it is suppressed. So much so that the heavy neutrino that is mediated, the mediator of neutrino mass generation, can be accessible to collider and can be produced by the associated Z prime, which could lie also at the TV scale. So one has Drellian production of the neutrino mass fermionic mediator particle, and that is perfectly consistent because, as I said, this VEV of this capital phi is an induced vacuum expectation value. And as I said before, also in this case, this is accompanied by charge-lepton flavor violation, instead of supersymmetry. And in this case, it is remarkable that besides the standard lepton flavor violation, for example, mu to E gamma decay, or mu to 3 electron, or mu to mu E conversion in nuclei, or tau to 3, whatever. Besides this, one has this novel type of lepton flavor violation involving the emission of a light or massless Goldstone boson G, whose profile is given here. And in fact, this kind of funny lepton flavor violating process would be more sensitive than mu3 gamma, because you can see here the allowed parameter values that are associated with different values of the relevant Yukawa coupling. They are shown here in this color code, whereas the sensitivity of the Goldstone mode is indicated by this red line, and the sensitivity to mu2 gamma is indicated by the vertical red line. So you see that this is already eating up a chunk of parameter space, whereas mu2 gamma is not. And there are the projected sensitivity for lepton flavor violation with Goldstone boson emission will become tighter in the future. There is a proposal by the Japanese experiment to bring this line even lower down. So this concludes my discussion of various Scotto-seesaw realizations and various realizations of dark-seeded seesaw mechanisms, all with physics lying at the weak scale, basically. Now I go back to the Scottogenic as proposed by Ernest Mach and by Tao. They proposed a really beautiful idea, these guys. That is definitely, they have the credit for that. Unfortunately, though, the model proposed is not fully satisfactory. And for that reason, people have revamped the construction to make it satisfactory. And in this revamped Scotto-seesaw mechanism, one adds not only fermionic singlet, but also fermionic triplet. And this is very much like supersymmetry. The fermionic singlet is like the binu. The fermionic triplet is like the neutral winu. And one needs also to add a scalar triplet boson. The presence of this scalar triplet is crucial to make this theory fully satisfactory from the symmetry point of view, first of all, and from the phenomenological point of view, because in this case, one can have three-level nuclear recoil, a spin-independent nuclear recoil of fermionic dark matter. Notice that here I'm talking about fermionic dark matter, very much like the neutralino in supersymmetry. In fact, this is just the neutralino dark matter phenomenology stripping out supersymmetry completely. Okay? As I said, the F is like the binu, the sigma is like the neutral winu, and there are no Higgs-inus, and there are no selectrons and no staus, nothing of that. What you have instead, in a complementary fashion that I already mentioned, are charged lepton flavor violating phenomena. But to convince you that this is a consistent theory of dark matter, I show here the relic density plotted versus the dark matter mass. This would be the fermionic dark matter mass, showing that you can have this region in green totally consistent phenomenologically and reproducing the value of omega h squared indicated by the Planck result. And in the presence of co-annihilation, you can get an even broader consistent range of dark matter masses, starting at much smaller values, even below 100 GeV. Concerning nuclear recoil direct dark matter detection, this is just, as I said, cold wind dark matter detection, probed by the spin-independent nuclear recoil cross-section, plotted here versus the dark matter mass. In color, the dark color down below is the neutrino floor, that is unbreachable at the moment, and the green region above is already ruled out by the current generation of experiments that I mentioned, Xenon, Panda, and Lux. So the region of interest is the white region in between. And you can see that this region is fully populated by this model. So you can have all the dark matter studies that you do in supersymmetry, you can repeat for this scenario, which is substantially simpler. And of course, the theories are inequivalent because all these phenomena would be unaccompanied by the presence of supersymmetric states, but they are accompanied, for example, by a lower bound on DVD. DVD here has a lower bound because I have only 2 new fermions added. One of my light neutrinos is massless, so I have a missing partner, radiative seesaw, which is just the scotogenic diagram. And in that case, one of the neutrinos is massless, and I have a lower bound for DVD. And moreover, I have a whole bunch of lepton flavor violating processes that could be there. And that would be able to distinguish this dark matter picture from a supersymmetric cold dark matter WIMP scenario. So these models, in principle, are distinguishable. Now, a word about seesaw mechanism again. I mentioned that dimension 5 is not a characteristic feature of Majorana neutrino. If you look this diagram down here on the right, you see that you have dimension 5 here for Dirac neutrino, okay? Dimension 5 operator for Dirac neutrino mass generation. So dimension 5 does not imply Majorana. You can have dimension 5 for Dirac. You can have dimension 6 for Dirac, dimension 6 for Dirac. The difference with Majorana construction, I mean, it's equally consistent. It's just a little bit more complicated, but the ideology is the same. One needs symmetry protection. In this case, a double protection. A protection for the small neutrino mass and a protection for its Diracness. So these are different things. But it is possible, all these blue references that you read, they are references either on UV complete constructions with Dirac neutrino masses or just operator classification. In particular, I mentioned here that the underlying symmetry behind the Diracness of the neutrino can have a high pedigree. It can be just a Pechi-Quint symmetry, can play this role. This was considered in this paper here. Okay, now I turn gears completely and I go to collider physics. We hope particle physics will have a future. Particle physics does have a future already from the neutrino side. We have a whole bunch of accelerator neutrino, a long baseline experiment. We have a coherent neutrino scattering experiment, and we have reactor neutrino experiments such as Juno. So we have a whole class of experiments indicating a future for our field. But we also expect that particle physics will also have a complementary future coming from colliders. Proposals like ILC or CLIC or CEPS in China, they are there. Let's hope that one of them gets pursued. And then we have the FCC, etc. And of course, this is well recognized both in the States, this is the P5 panel recommendation last year, and also the very recent recommendation in Europe by the Future European Competitiveness Report. They both push very hard for an FCC-like process. So the question one can pose is, can I learn about neutrinos at such energies? Can I get complementary information on neutrinos? And the answer is yes. And to illustrate this, in the simplest possible fashion, I go to our original seesaw mechanism that we call type 1 and is now called type 2, and I prefer to call the triplet seesaw. This is the simplest seesaw because there is only one Yukawa matrix that determines everything. It determines the neutrino mass, and it determines all the associated phenomena. So it has been shown recently, 2 years ago, that this seesaw can be fully reconstructed just using experimental data. And it can get a projection in the domain of high energy collider experiment. And this is illustrated here. This would be an E plus E minus collision at 3 TeV center of mass energy, which would produce a 4 muon final state. So you see, first of all, we are talking about cross-section in the tenths of femtobarn. This is not too small. And you can see something very remarkable. The size of this cross-section correlates with the mass of the lightest neutrino, because it's the same physics. It's just one Yukawa coupling matrix. So from experiment, I already have the limits from the Catherine experiment, tritium beta decay, and I have the cosmological limits on the lightest neutrino mass. These are illustrated by the black bands, the vertical bands that you see, the gray bands, vertical bands. Everything to the left of these bands is unexplored territory. So you can study this cross-section, you can measure this 4 muon signal. And you see this remarkable feature that not only it correlates with the value of the lightest neutrino mass, but also it differentiates, for this particular example, normal from inverted mass ordering. This is very remarkable. This is not difficult. It is not easy at all to differentiate strongly the neutrino mass ordering by neutrino quote-unquote experiments. Juno was designed for that, but it will not settle the issue. You need to combine Juno with other experiments, all of which they are still, some of them in the planning stage, such as neutrino telescope. Of course, they are advanced in a very healthy manner, but we are talking about at least the next decade. So here you have, it is not completely stupid that you can do this differentiation at high energy collision. You can even go one step further. Instead of having a 4 muon final state, I can strip off 1 muon and substitute it by an electron. So I have a 3 muon and an electron final state. So this violates lepton flavor. And you can correlate the magnitude of this cross-section. It's a little smaller, but not too much. Less than an order of magnitude, smaller than the previous. But now I can correlate it with the branching ratio for mu to gamma. And you can see very clearly the vertical band is ruled out by Meg. Everything to the left of that band is unexplored territory. So you can discover charged lepton flavor violation in the domain of high energy physics, of collider physics. So colliders can provide the discovery site for charged lepton flavor violation. And in addition, like before, you may be able, if you are lucky, to probe normal from inverted mass ordering. This is, of course, type 2 seesaw, so-called now type 2. Type 1, the same thing. In fact, this subject has a very long history. In fact, this was proposed, published in 1990, so it is 34 years ago, the age of Jesus Christ, 1 year more. It was suggested in the pre-LEP days that a Z0 could decay to a heavy neutrino and a light neutrino, giving monojet events. So we have the decay product of the heavy neutrino recoiling against missing momentum. So the sensitivity to the relevant coupling strength is indicated here if you have a million Z0, and would enable you to probe heavy neutrino masses up to the mass of the Z, because it's single production. Of course, after this proposal, all the lab collaborations checked for that and nobody saw it. So now this possibility of type 1 seesaw mediator production from a gauge portal is revived now from the point of view of a Z prime gauge portal, in which case you pair produce the heavy neutrino from a Z prime, and this plot here on the left, for example, by just gauging lepton number, as I described previously, and you see here in dashed the sensitivity provided by mu2 gamma search, and in blue, the sensitivity provided by collider search, illustrating how, again, collider can provide a discovery site for charged lepton flavor violation, even for type 1 seesaw, which is definitely more complicated than the triplet seesaw. Another possibility, again, low scale type 1 seesaw, the linear seesaw, you don't need to go through a Z prime. Z prime means you have to extend the gauge symmetry. You can just go to the linear seesaw mechanism. There you find the leptophilic Higgs. So the associated Yukawa coupling YS allows you to pair produce this is quasi-Dirac neutrino. So it is the NN bar production. This is the cross section, the NN bar production cross section for different values of the charge Higgs exchanged in the T channel. So you see that you have a quite healthy cross section of tens of femtobarn. So this is not a small thing. Once produced, the heavy neutrino mediator, it must think, should I decay immediately? This is the decay length versus the heavy neutrino mass, or should I oscillate? And I can oscillate from neutrino to anti-neutrino, because after all, it is not a Dirac neutrino. It is a quasi-Dirac neutrino. It's like the KK bar oscillation. So this neutrino to anti-neutrino oscillation, in the simplest scenario, in fact, they are directly correlated with the solar and the atmospheric splitting that you measure in the oscillation data. And they allow you to produce the same signature we had before for jet plus dilepton, but with the same sign dilepton. And this is fantastic because same sign dilepton is a signature of total lepton number non-conservation. So this also means that high energy collider may provide the discovery site of lepton number non-conservation instead of DBD that I discussed before. Thanks to this NN bar oscillation phenomenon. This is the number of events that you would expect, 10,000 events for heavy neutrino mass in the around 100 GeV. So this is, I think, interesting. I don't know how am I doing on time, Antonio?
You are in time, and we have flexibility.
Okay,
So we have a start time.
I will say a few things about theoretical theory now. One of the biggest issues in particle physics is to understand the flavor problem. The standard model does not explain the number of flavor, nor the pattern of lepton mixing, nor the pattern of quark mixing, nor the spectrum of fermion masses. This is the biggest problem we have in physics. Nobody has a solution to this problem, but I want to highlight the legacy of oscillation. Namely, oscillation have not only discovered that leptons mix, that flavor is violated in the lepton sector, but also that it is violated differently from what we see in the CKM model of the quarks. That is a very important thing. Nobody has an understanding of that. And likewise, nobody understands why the muon is 200 times heavier than the electron, or why the top quark is so heavy. This has made people crazy trying to explain this from some sort of symmetry principle. And I cannot put all the references to the attempts that have been made over the last 20 years, but I can at least flash a subset of attempts, which I indicate here in blue, which have as a common denominator the fact that in trying to explain the pattern of neutrino oscillation in what concerns the mixing, they have given as a byproduct this beautiful bottom tau unification mass relation that I call the golden relation. It has nothing to do with SU5. It has no gut group whatsoever. It has just the standard model cross family symmetry. And the relation itself, which is very good, involves fermion of all the three families, both for the lepton as well as for the quarks. So I think this relation will eventually go to the textbook. But certainly it does not explain the totality of the fermion mass hierarchy problem. This is illustrated here. Neutrinos are completely different from the rest, maybe because of seesaw, of radiative corrections or whatever, but then you have this mess up here, and certainly we have no clue, no complete understanding of this pattern. But I have one relation which came as an unexpected byproduct, which is very good. So I make two statements. The first is this relation may be part of the truth. First comment. Second comment is that perhaps the ultimate solution to the flavor problem requires us departing more radically from our gauge theoretical principle, using four-dimensional field theory, and assuming, for example, the existence of extra space-time dimension. And an attempt that has been made here is in terms of six-dimensional orbifold. This construction has something nice about it, namely, out of the isometries of the six-dimensional theory, after you compactify it on a torus, you are bound to have an A4 family symmetry in 4 dimensions. It's fixed for you. This fix is a problem because this gauge model building for introducing family groups, and Antonio Cárcamo knows that very well, he's one of the champions of those attempts, is a very arcane subject. You have to try group to group, from representation to representation, completing this, completing that to make things work, because you don't know the symmetry. This way you determine the symmetry. And you have, as the first prediction, our beautiful golden relation that you can see here expressed as a prediction for the strange and down type and down quark masses. This is this blue band. And from experiment, you have these boxes. So you see everything is very consistent. We also have neutrino predictions. For our ignorance plane, this is the CP, delta CP versus the atmospheric mixing. And the prediction from the theory is the dark magenta points, and the results from a general global oscillation fit is the light magenta points. So you see everything is consistent and there is prediction. Also for DBD, there is prediction. But we have only one prediction for the mass spectrum. We have a nice, we know the group, but we cannot completely solve the fermion mass hierarchy problem. I mentioned one more comment here that I told you about the golden relation. Here is the golden relation. Some new comment about the golden relation. I will just show you the plot. What you see here in this dash, in the lower right plot, the dash curve, is the standard golden that I just showed you before. But here you see a blue curve. This is a new golden formula that is corrected with respect to the old golden by this extra -3 here that you see in the denominator. And this golden arises from a recent model that was considered, which you can see here in JHEP, using an S4-based theory. Again, you have to put the family group by hand, but you have modular symmetry correction to the golden. And you see they are both allowed, but there will be some competition to see here which golden is best. But as I was saying, this framework gave me the symmetry, but it cannot explain the total Fermi mass hierarchy problem. As a possibility to go in that direction, I appeal to the proposal of Lisa Randall and Arkani Hamed. They proposed a solution of warped dynamics to explain the gauge hierarchy problem. What I'm suggesting is to go from their warped dynamics to a warped flavor dynamics to explain flavor mass hierarchy for the fermion as well. I don't know the answer. This is a problem for mathematicians to coin the right geometry. What I can do as phenomenologist, and we did, was a simpler problem, namely to show that it is consistent, the imposition of family symmetry in a warped flavordynamic scenario is consistent. It's consistent mathematically, consistent with Einstein's equation, and consistent and predictive. In fact, for this particular construction, we took the tip-fry family group, which is just the double cover of A4, and we showed that we can have very simple analytical prediction for the neutrino mixing parameter that you can see here, which was known before. This is the so-called TM1 neutrino mixing pattern. It was suggested just out of the blue, just as a phenomenological thing. Here it is derived from first principle, and it is shown there, the tight prediction on the, what I call the ignorance plane, delta CP in modulus versus the atmospheric mixing, very tight prediction compared with the experimental determination, the vertical line. And likewise for DBD, you have the two tight prediction depending on normal or inverted neutrino mass ordering. In this model, we have TM1 as a prediction and Majorana neutrino as a prediction with large DBD. There is another construction based on a different gauge theory, a family group, which instead of giving Majorana neutrino, it gives Dirac neutrino. And instead of giving TM1, it gives TM2. I just leave you with the references. So this brings me to the conclusion. The discovery of the Higgs boson has not closed the standard model. It is not the last brick of anything. The discovery of neutrino oscillation is at least equally important as the discovery of the Higgs. Sorry for those that don't agree. And it has initiated a very rich program of oscillation experiment trying to determine the CP phase, the octant, the mass ordering, whether we have things beyond the minimal picture, such as unitarity violation or non-standard interaction. And last but not least, DBD search experiments. We have, at the moment, Kamlan-Zen with their final result. And we have now the successor of Gerda experiment, namely Legend. And we have also the Nexo proposal in US and other proposals based on molybdenum. They will shed light on whether neutrinos are Majorana or not. And then for the first time in history, we have the ability to probe the neutral current in neutrino experiment using the coherent neutrino scattering. So all we can do is to hope that this rich experimental program will shed light upon the biggest drawbacks of particle physics today: the dark matter problem, the flavor problem, the unification problem, the strong CP problem, and perhaps some of the existing anomalies that have been indicated by experiment. With this, I conclude. Thank you guys for your attention.
Thank you very much, Jose, for the very great and very complete seminar. Question from the audience?
I have a question.
Yes.
Just a moment. Yes.
Yeah, first, thank you very much, Professor Jose. Very nice, interesting talk. On that slide, could you go back to that slide in which you discuss
Which
the
number of
triplet?
slide do you remember?
I don't remember the number, but it's the triplets you saw, the collider
Okay, okay.
signature phenomenology.
I think. Okay, here.
Yes, this one. Yeah. Yeah, so as I can see from the plot, it seems that the production mechanism of the H++, you are considering a lepton collider, right?
Yes, for this example. You have similar, you can also do a hadron collider.
Yes, that's my
But
question.
this
If
is
this
neither.
kind of correlation has been studied in hadron colliders.
I have not done that, but I think one can do it, right? You can produce the Valle, you can produce the heavy neutrino, the heavy Higgs, and the heavy Higgs can decay leptonically in a hadronic environment.
Yes, exactly.
There is nothing preventing that possibility. But this is very neat. That's why I chose it.
Yeah, okay. Thank you.
I have a question. First of all, very nice talk, Jose. Thank you very much.
Sorry, who? I don't see who is asking.
Oh, me, Marco.
Ah, Marco. Yes.
Yeah.
Sure.
It's yeah. My question is about the same slide that you are showing. The label 3 TeV is the mass of the double Higgs that
Is
is
the
in.
center of mass energy.
Oh, what is the mass of the double charge Higgs? 1
It
TeV?
is, I don't recall, but it is consistent with experiment. We checked.
Okay.
We checked all the constraints.
Okay. Yeah, thank you very much.
More questions from the audience? Any more questions? Jose, I had a question regarding that slide plot. I was wondering why in the bed of the triplet you don't consider value up to 1 GeV, because as far as I remember, the oblique parameter constraint in the bed of the SU2 scalar triplet can allow to have the bed of the triplet up to few GeV.
Well, I like to be conservative with limits. I always like to be conservative with limits. I think 3-4 GeV is perfectly possible, and it depends to some extent on the hypercharge of the triplet. You can have zero hypercharge and no zero hypercharge. There is some dependence, but few GeV is perfectly okay.
But the result will not change significantly with the value, for example, for the cross-section.
Which you're talking about dark matter or what?
No, you're talking about that plot, the plot of this production cross-section. If you consider larger value for the bed of the triplet, it will not increase so much. The cross-section will be
No, not at all. I don't think it is relevant here. It is
I see.
relevant for our dark matter thing. It is relevant. There I consider two examples. That guy has zero hypercharge, so I consider 4 GeV and 1.5 GeV. They are both correct. They are both
I see.
And the differences. But this guy, this omega, is an omega that is a complete singlet. You see here. Well, sorry.
A triplet, yes.
It is a triplet. It is a triplet, but it is the hypercharge is different, right?
Yes.
The hypercharge is not. You see, this omega does not couple directly to lepton-lepton. Otherwise, you would not have a loop-induced mass.
Exactly, yes. Because
So
the
that is
symmetry was
forbidden by hypercharge.
correct.
So
I
in
see.
this case, 4GV is perfectly okay.
I had
And
another.
yeah,
Yes.
okay.
I had another question in this. What will be the in this? I suppose that in the similar way that the A4 growth can arise from the six-dimensional compactification, orbifold. What about the S4 group? It could also arise maybe from similar
That
compactification.
I do not know. I should be honest there. We did these constructions. We did the phenomenological models. We studied them quite perfect. This is really nice model for flavor. We have a complete flavor, a table with all the family of flavor observables, even in the CKM quark sector. Of course, there we don't predict much, but we fit. We have the quark lepton-golden relation. We have the neutrino predictions. We have everything. However, the mathematics of the construction was not really discovered by us. There were previous papers involving GATT construction by Steve King and this Mexican guy, our collaborator, Francisco de Anda. They were those that first noted that you may derive the family group as isometries of the higher symmetry, as you can fix. And we took A4 because it's the simplest, and that's what we took. There may be other alternatives, but they will be more complicated.
I see.
What I know is that the simple thing, we have, I think, 4 publications doing different models of dark matter, Kaluza-Klein dark matter, scotogenic dark matter, WIMP dark matter. We have many. They are all very, very much consistent, but there may be more in the general mathematical picture that we have covered. And I refer you to the earlier paper of De Anda and Steve King.
Thank you, Jose. I had another question in your paper with Leite and another person in which you had a small induced bed for the SU2 scala, in which you compute also the prediction in this mu2 gamma, mu2 Goldstone.
You
What
mean
about
this one?
this
You
one?
mean
Yes,
this?
this one.
The
This one, yes.
Scottish is all with gauge lepton number.
Exactly. This one, what will be what about the prediction regarding, for example, electron-muon conversion processes, or for example,
We have not done that. We are studying a little bit that right now. We are studying lepton flavor violation in this model at this very moment. We do not have a complete map of that, and it is not very easy to get it. Especially, well, for the leptons, it is easy. But if you want to understand also the quark sector, because this model contains quarks,
Yes.
then you need also BS transitions, penguin diagrams. You need the complete Burras-like approach. And we are there. We are trying to make progress in that direction. Probably my hunch is that it will not be that interesting for the quarks. The interesting will be mainly for the leptons. But still, this is very, very promising, this plot here that you see.
Yes.
Mu2 gamma, mu2 gamma is in the horizontal, mu2 Goldstone is in the abscissa, in the ordinate. So it is more sensitive. The process is just a two-body decay. So it is a distortion on the Michel spectrum of the muon. And you can measure that distortion better than you can measure mu2 gamma itself. And this is the current bound. It's already more constraining than mu2 gamma. And it will become better in the future. Of course, mu2 gamma may go to the left also, but this will go down.
I see. Mu2 conversion constraint, they are weaker, I suppose.
Mu2 conversion, you can do everything. In fact, we may do it. We are in the middle of it.
Very nice.
Usually, mu2 gamma is more. usually mu to E gamma is more restrictive, not always. Sometimes mu E conversion or mu to 3 depends. To be honest, I don't know the answer. We computed the simplest thing, the most obvious thing, and that was mu to E gamma.
I see.
But we have a complete map. Here we included a complete map. This is for scotogenic model. You have more things. In fact, these things are what forbid the absence of points to the left of this is due to these bounds. To the left of
Very
this.
nice. It's correlated with dark matter.
Which show that you have a WIMP dark matter model that is not probed by searching for supersymmetric states. It is probed by searching for charge lepton flavor violating, because it is related to neutrinos, not to supersymmetry. Of course, I have nothing against supersymmetry. That's also an interesting, but as Comrade Mao Zedong would say, let all the flowers bloom. Supersymmetry is an alternative. This is another alternative, which brings the new physics to accessible scale, answers many of the issues, in this case, the dark matter issue, and the neutrino mass generation issue in a very attractive manner, but does not fix everything. Supersymmetry also does not fix everything. You have to impose R parity by hand. You have to do many things in an ad hoc fashion. You have no idea of the pattern of SUSY masses, of the pattern of SUSY break in couplings. It's all at your disposal. To me, it's a much more complicated construction.
Yes, I see. Thank you so much, Jose. Any more questions from the audience?
Yes, I have a question.
Yes.
Hi, Jose and Nicolas, PhD student. I have a question that is, I think, is more fundamental and for education purpose. So I think the most important thing, or one of the most important things of flavor physics, is the nature of neutrinos. So will neutrinos be Majorana or Dirac? So my question is, what
But
about
that may not do anything, may not have anything to do with flavor.
Okay.
You see, in fact, I made this stress, the complementarity and the role of lepton flavor symmetry versus lepton number symmetry. In some sense, lepton number symmetry has to do with the Majorananness, with the masses. And lepton flavor symmetry is something else. It's completely complementary. In our massless model, the template model, which forms the basis of the low scale seesaw, the 3,6, in the symmetry limit where lepton number is conserved, neutrinos are strictly massless. And precisely for that reason, lepton flavor violation can be maximal because it is unconstrained by the limits on the massiveness of the neutrino.
Okay.
It's constrained only by electroweak precision data. And in that case, universality of the weak interaction.
Okay, so in that direction, if neutrino are Majorana, so everything just stands as it is. Just.
I mean, the main result to distinguish Dirac from Majorana is the black box. And everything related to the black box. And I gave you an example of a completion in which high energy collider could be the discovery side of lepton number and also of lepton flavor, but they are kind of independent.
Okay. Okay, thanks.
Any more questions from the audience?
I mean, people always ask, why prove that neutrinos are Majorana? This is not correct. The dimensionality of the operator responsible for neutrino mass generation has nothing to do with the ultimate nature of neutrino. It can be Dirac, can be Majorana, can be anything. The only thing one can say is that in the Majorana case, it's neater because there's just one operator. The construction is less Baroque. But Dirac seesaw is equally consistent and can be related, for example, with the Pechi-Quinn symmetry, which can be an unexpected relation to the quark sector. And another drawback of the standard model, understanding Pechi-Quinn and the strong CP.
Okay. Okay, thanks.
More questions from the audience? If there are no more questions, we thank Jose for the very nice and very excellent seminar. Thank you so much, Jose.
Thank you
Thanks a
very
lot.
much for the invitation.
We see you at the next seminar. Jose, are you coming to the head conference?
Unfortunately, I
January?
cannot. January is a bad time for me. That's why every year I miss the HEP conference. I just went once, which I made a big effort, and I went both to the HEP conference as well as to the school, and I also lectured at the school. And for me, it was the last time I saw our friend Schmidt.
Yes.
Unfortunately, I will miss his celebration this year.
Yes, because this period of the January, it may be
Because
holiday.
the period of January, I'm completely busy
Understand.
with personal trips and other trips, especially personal. I mean, family trips to two different locations. So usually that time I don't travel.
Understand. There will be other occasions, Jose, because you used to have this conference every 2 years.
Sure. Sorry, I see that there is my face is very dark.
It's
Okay.
getting, yes, it's very late yes, it's evening there in Spain. Had a very nice time. Thank you so much, Jose.
Thank you for the invitation. Ciao, ciao.
Ciao.
Bye.
Ciao.
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 Thank you. Ciao.
Ciao.
Ciao.